everyone. So to start the afternoon session, we're happy to have Jacob Lurie talk about rationalized Syntomic Cohomology.
All right, thank you. So my talk today is about the theory of Syntomic Cohomology. So this came up in today's lecture, but let me just remind you of maybe well, something he already said, which is this theory of Syntomic Cohomology. Well, it's an invariant which takes in something like a p-adic formal scheme and outputs some cohomology groups, which I'll write as h star of x, dp of n coefficients. So n is some number that refers to as the weight. And you're supposed to think of these as a replacement for p-adic etale cohomology. In situations where p is not invertible on the base. So here I'm going to be interested in a purely p-adic situation where p doesn't vanish. Where p vanishes at every point. So x is a p-adic formal scheme. And these can be realized as the cohomology groups of a certain complex, which I'll write as R gamma, x with zp of n coefficients. And most of the statements that I'm going to make are going to be at the level of this chain complex. So this is an invariant that has a long history going back to the work of Fontaine and Messing in the 1980s. But the definition that I'm going to be talking about is a relatively recent definition. So this was introduced a few years ago in the work of Bott and Schultz. And so their original definition of this was they found these syntomic complexes as certain graded pieces in the topological cyclic homology. The topological cyclic homology is some invariant that's closely related to algebraic K-theory. And what they did is write down a filtration on this invariant. And then they said that the graded pieces were some kind of p-adic version of etale cohomology. They made this a definition. So this is a sort of a topological definition, or it comes from homotopy theory in the sense that this TC of x, it's a spectrum, so not something that comes to you as a chain complex. But this was re-expressed in a purely algebraic way in follow-up work of Bott and Schultz, using their theory of prismatic cohomology. So another definition from that point of view is that R gamma of x zp of n, well, I'll just put it in quotation marks. This is the fixed points of Frobenius on the prismatic cohomology of x. Well, some twisted version of the prismatic cohomology of x that takes into account the weight that you're interested in. But there's a sort of third, more recent definition, which is a point of view due to Drinfeld, which is that this R gamma of x, it's something that you can understand as computing coherent cohomology, not of x, but of a certain algebrogeometric object, certain stack that you associate to x. So following the course that Bhargav gave on this last year, I'm going to denote this by, so this is the cohomology of an object that I'll denote by x sin with coefficients in its structure sheaf twisted by a certain line bundle. On this object, there lives a certain line bundle, and you can take cohomology with coefficients of the powers of that line bundle. So these are three definitions. I'm not going to talk too much about any of the definitions. What this talk is going to be focused on is maybe making this more concrete. So if you're someone who has never seen these invariants before, but is familiar with a lot of related invariants, things like the Rham cohomology or crystalline cohomology, what this talk is going to be about is describing what syntomic cohomology is in terms of those more familiar things after you invert P. So let me begin by doing that in a simple example. So let's say K is a perfect field of characteristic P, and X is some smooth variety for K. Then, if you're familiar with the theory of crystalline cohomology, there's a very simple description. Well, first let me make a definition. If I write R gamma of X with two p-adic coefficients, this means R gamma of X with z p-adic coefficients, and then you invert P. So what is that in this case? Well, in this case, you have the theory of crystalline cohomology. So you can look at the, let me actually call this X0, because I'm imagining this really arises as the special fiber of something that I'm really interested in, which is some kind of mixed characteristic object. So this is an object in characteristic P, and in characteristic P, you have the theory of crystalline cohomology. Look at the crystalline cohomology of X relative to the bit vectors of K. And I want to work rationally. Well, let me take that and invert P. And this has an endomorphism, which is just induced by the Frobenius endomorphism of X. And that endomorphism is actually an automorphism once you've inverted P. And you just take the phi equals P to the n eigenspace of this, but in the sense of the derived category. So this is a chain complex, and what I mean by this is the fiber of the map phi minus P to the n from this chain complex to itself. So more informally, it's the part of crystalline cohomology where the Frobenius acts by multiplication by P to the n. And so the question that the rest of this lecture is devoted to answering is, what about smooth, say, what if X is a mixed characteristic? The fixed idea is, let me write capital K. This is going to be a complete, discretely valued field mixed characteristic. And I'm going to write little k. It's the fraction. First, OK is its valuation ring, and little k is its residue field. And I'm going to assume that little k is perfect. And let me just state in this context the name theorem which answers this question. And let me first state it in a sort of nice geometric situation. So the theorem that I'm going to talk about, which has been Antieau-Mathew-Morrow and Nikolaus. So let's say that X is smooth and proper. Sorry, so this is maybe preliminary version of their theorem. Let's say if X is smooth and proper scheme over the ring of integers at K, you can look at the syntomic cohomology of X, by which I mean the syntomic cohomology of its p-adic completion. And let me write X0. for the special fiber. So it's X space change to spec K, spec of little k. So whatever this complex is, it's going to map to the Syntomic cohomology of that special fiber. And I've already told you what that is. And actually, sorry, I want to state this QP coefficients for now. I've told you what this is. This is what you get when you look at the crystalline cohomology of F0. And you take the eigenspace where the Frobenius acts in the way dictated by the weight.
And you invert P.
Sorry?
You have to invert P.
I didn't hear you.
You're only inverting P on the
I equals P to the N?
1 over P.
You're working on the rational.
1 over P.
It's underneath pi to P to the N.
Yes.
Right.
Oh, sorry, yes. Yes. Thank you. We're doing this rationally. Okay, so let me assume for simplicity that the ramification index is less than P. So in that case, here to talk about crystalline cohomology, I'm using that the bit vectors of K, the maximum ideal has divided powers. But if the ramification index is less than P, that's also true in the ring of integers OK. So this actually maps to, well, the same expression. We say x0 now relative to OK. And let's forget Frobenius invariance. And this is just the de Rham cohomology of the entire variety. Or since I've inverted P, it's the de Rham cohomology of the generic fiber. So let me write that. This is R gamma of xk with coefficients in its de Rham complex. So whatever this Syntomic cohomology is, it maps to de Rham cohomology of the generic fiber, but there's something a little bit better than that, you can say. It lands in the nth stage of the Hodge filtration. So this factors through R gamma of xk with coefficients in, I'll write it as omega greater than or equal to n xk. There's a commutative diagram like this, and the theorem is that this is actually a pullback square. In other words, you can compute rationalized Syntomic cohomology in terms of more classical invariants by thinking about the crystalline cohomology of the special fiber, the way Frobenius acts on it, and the de Rham cohomology of the generic fiber and its Hodge filtration. So maybe I should remark, from the original point of view of Fontaine-Messing, at least when K is QP, this is almost a tautology, or maybe it is a tautology. This is sort of how Syntomic cohomology was defined. But from the point of view of these new definitions, it's not a tautology anymore. Or from the original point of view, maybe the interesting statement isn't this theorem, that's the definition of the upper left-hand corner. But then the question is, why is this an interesting invariant? Why is it related to other things you might care about, like algebraic K theory or the etale-cohomology of the generic fiber? And from these more recent points of view, the first one, it's sort of by definition something that's closely related to algebraic K theory. But then the question is, how do you compute it, or how do you understand it in more classical terms? So either way, there's something to learn here. So let me give some examples of what this is saying. So this is a fiber sequence, or sorry, a homotopy pullback square in chain complex. So more concretely, what that means is that you have some long exact sequence of cohomology groups. So you get a long exact sequence, which I won't write out in detail. But with a let me focus on the interesting part, which is a boundary map. The boundary map goes from, let's say, n is the weight, so let me not use n for that. H star of the de Rham cohomology groups of the generic fiber go into the Syntomic cohomology groups of X with a change in degrees by 1. This appears in the boundary map of a long exact sequence, and actually this map is an isomorphism if the other two terms in this diagram are both 0. The one way that can happen, as soon as n is bigger than the dimension of X, this term is 0, right? Because differential, you have no forms of degree greater than n if X only has dimension n. And this term also goes away. So this is an isomorphism, let's say, if n is greater than the dimension of X relative to OK. And furthermore, well, I told you, Syntomic cohomology, it's supposed to be some replacement for the theory of p-adic etale cohomology. When X is proper, this maps to the etale cohomology of the generic fiber. Xk with 2p coefficients. And this map is an isomorphism if n is a little bit bigger. This is an isomorphism if the weight is bigger than the dimension of X plus 1. And so if n satisfies that second inequality, you are learning something about a relationship between the de Rham cohomology of the generic fiber and the etale cohomology of the generic fiber.
Maps to H etale star or H etale star plus 1?
What's that?
H star etale.
Oh, it's star plus 1. Thank you. So let's just do a sub-example. Oh, sorry. Hotel something, 227. If that's you, your card is up here.
Yeah.
Well, let's just do a sub-example. Let's take X. This back okay. And in that case, this etale cohomology, that's just the Galois cohomology of the Galois group of K. So what you're learning is that if n is greater than or equal to 2, well, the Galois cohomology, Galois group K bar for K, QP of n coefficients. This is just like K if star is equal to 1 and 0 otherwise. So like if K is QP, this is something you could see using class field theory, that these H1 cohomology is one-dimensional in degree 1. But it's a special case of what this result is saying. So let me, I said that this was going to be a preliminary version of the major. Let me start massaging it a little bit, closer to what the way that they said it and what we're actually going to prove. So first of all, almost all of the hypotheses that I've mentioned here are not important. So first, I said X was proper, and that's only because I wanted to think of it as a scheme. So let me erase the word proper and say that this is a formal scheme over its both function. And then, well, I originally told you Syntomic cohomology is an invariant of formal schemes. And here, so I can write this as Syntomic cohomology again. Now, I shouldn't call this the de Rham cohomology of the generic fiber. This is a formal scheme, but what I can write is a formal scheme which is smooth over OK. I can take the de Rham complex of X over OK. And let me put a little hat on top of that to remind you, X is a formal scheme, so everything is p-adically complete here. And after I take the cohomology of that de Rham complex, I invert P. And you can do the same thing at some stage of the Hodge filtration. So if I say it in this way, that it's now irrelevant whether X is proper or not. And it's actually also irrelevant whether X is smooth or not if you're willing to talk about derived de Rham cohomology. So let me erase the word smooth. Still talk about the Syntomic cohomology of X. Let me assume that X is at least flat over OK, so that there's no ambiguity what I mean about the special fiber, which also has its Syntomic cohomology. And the difference between the two is something that's controlled by a version of the Rham cohomology, but now it's the derived Rham cohomology. I'll put a little L here to remind you that it's been. I should erase the K here. Derived Rham cohomology of X. And this is now something that's good no matter how bad the singularities of X are. And let me just make a remark that if you're willing to contemplate X's which are not smooth, the base becomes irrelevant. Without loss of generality, you can take K to be QP if you want. The content of this theorem, when you view X as an OK scheme and when you view it as a ZP scheme, well, there's a little bit of argument needed to justify it, but the theorem is saying the same thing. So let me give an example to this is an interesting theorem in the case where X is something that has singularities.
Can we erase the ramification index then?
Yeah, so the only place that I wanted to write that because I wanted to explain why there was a map from here to de Rham cohomology. If the ramification index is small, there's a map even before you invert P. And otherwise, you have to say a few words about it's not defined integrally, but rationally, it's still well defined. And
Yeah.
okay, so without loss of generality, K is QP, X can be very singular. Let me give an example of how that could be interesting. So let's let C be a completed algebraic closure. QP. And now I'm going to let X be the formal spectrum of the ring of integers at C. So I've kind of stated this theorem as giving you some way to compute Syntomic cohomology in terms of more classical invariants. But in this example, you can kind of read it the other way. So this is an example where Syntomic cohomology is very simple. Syntomic cohomology, it always maps to the etale-cohomology of the generic fiber. In this situation, that map is just an isomorphism as long as n is non-negative. That upper left-hand corner is just a copy of QP. So actually, it's a copy of QP, not canonically. It's a one-dimensional QP vector space on a generator that I'm going to call T to the n. So what are these other terms? So this term over here says, take this ring OC, reduce it mod P, and then take the crystalline cohomology of that. So that's one of Fontaine's period rings. That's the ring E-Cris plus, if I'm remembering correctly. And well, to get the Syntomic cohomology, you take the part of that where the Frobenius acts by C to the n. And now we can compare this to the de Rham cohomology of that ring OC mod P. And now if people wanted to be really pedantic, if people were really in the know and wanted to be pedantic, they could say something like, Jacob, if you're going to talk about derived de Rham cohomology, do you mean the Hodge completed version or the non-Hodge completed version? And the answer is it doesn't matter, because this statement is really about the difference between the nth stage of the Hodge filtration and the entire complex. So completing with respect to the Hodge filtration, it doesn't change that difference. But let me use the Hodge completed versions of rational de Rham cohomology here. So if you take the Hodge completed de Rham cohomology of this ring OC mod P, that's another of Fontaine's period rings. That's the ring E de Rham plus. Yes, I first learned this from a paper of Sasha. It's here. And well, in terms of that identification, the Hodge filtration on B de Rham plus is just its B de Rham plus is a discrete valuation ring, it's the filtration by powers of its maximal ideal. So the nth stage of the Hodge filtration is, I've conveniently named my generator in Syntomic Cohomology T to the n. And here T, under this comparison map to de Rham cohomology, goes to a uniformizer in B de Rham plus. And so here you have T to the n times B de Rham plus. And the statement is that this is a homotopy pullback square of chain complexes, but that's a very concrete statement in this case. So what's the upshot? So this is telling you concretely two things. The first is that you have an exact sequence of abelian groups. 2p goes by multiplication by t to the n. To the part of B plus where the Frobenius acts by t to the n. And the co-fiber is B de Rham, or the co-kernel is B de Rham plus mod t. Now it's saying a little bit more than that because remember when I wrote this superscript phi equals p to the n earlier, I meant you were taking an eigenspace in the derived category, meaning you were taking the fiber of a certain map. So here I'm implicitly just taking the kernel of that map in the usual sense. But what this a priori would say is that you have a fiber sequence. But since this is in degree 0 and this is in degree 0, it's telling you that this term also has to be in degree 0. So the other thing that you learned is that the map phi minus p to the n as a map from B plus to itself. This map is surjection. So the first of these statements is the fundamental exact sequence, p-adic. Maybe it's called that when n is 1. And it can be viewed as an instance of this theorem. Okay, so well, sorry, maybe I should say a little bit more about how you can think about this, what this theorem is saying. Let me go back to the situation where X is smooth and proper over OK. So the upper left-hand corner is this theory of Syntomic cohomology. There's another way that you can access that, or another definition of that, in the case where X is very nice, which is Syntomic cohomology is the étale version of motivic cohomology. It's what you get when you take motivic cohomology, you complete at the prime P, and you force it to satisfy descent for the étale topology. So from that point of view, it's something that you can think of as not too far from algebraic cycles. And you can think about the map from the upper left-hand corner to the lower right-hand corner. It's some kind of cycle class map. It's something that takes something related to an algebraic cycle and produces a class in de Rham cohomology from it. And so from that point of view, what this is addressing is the question of, given a class in de Rham cohomology, when might you hope to see that it comes from an algebraic cycle? And the theorem is saying, well, there's two things that have to be true. The one thing that has to be true is the kind of condition that you see in the Hodge conjecture. If you have a de Rham cohomology class and you want it to come from a cycle of codimension n, it had better belong to stage n of the Hodge filtration, which is saying that it lifts along this map. But there's also a condition that appears in the Tate conjecture, which is if you take this de Rham cohomology class, we think of it as a class in the crystalline cohomology of the special fiber. If it's going to come from an algebraic cycle, then the Frobenius has to act on this by the appropriate power of p to the codimension of that cycle. And what the theorem is saying is, well, if you have a class in de Rham cohomology and it satisfies both of those conditions simultaneously, then you win something. What you don't win is an actual algebraic cycle. What you win is a class in Syntomic cohomology, which, roughly speaking, is saying something like, etale-locally you can p-adically approximate by algebraic cycles, something heuristically like that. And in that form, there are some earlier incarnations of this theorem that I should mention. So there's a, I can say also, version of the block. we know there's some alternate proof given by Bailenson. So they invented something, if I remember correctly, that they called continuous Chow theory, which is some attempt to capture to make precise what I was saying about approximating by algebraic cycles. And they proved some statement like this. So the rest of this lecture, I'm going to devote to sketching for you a proof of this theorem. And the proof that I want to sketch is going to be, I think, very different in spirit from any of the preceding proofs. So, at least in my understanding, all of the preceding proofs of this theorem heavily exploited the fact that Syntomic Cohomology is something related to algebraic K-theory. And they used ingredients coming from homotopy theory. So I want to sketch a proof for you which doesn't use those ingredients. And also, this proof is, it's a rational statement. If I didn't invert P, the statement would not be true. But the proof that I'm going to give you is going to be something which really lets you control how far it's off from being true integrally. Any questions before we get started?
So do you allow general coefficient for the QPN replaced by something?
Yeah, so it's going to be a theorem about prismatic F gauges, although I'm not going to.
Okay, all right.
Oh, sorry, I mean arbitrary coefficients, like arbitrary crystalline coefficients.
Okay.
Okay, so I already told you step one was to say, without loss of generality, field K is QP, the absolute case. But I don't want to work with QP. Step two, I want to say, without loss of generality, K is the field QP adjoin zeta P. I want to add a primitive P through to unity. And, well, what's the proof? So, for X defined over ZP, consider Y, which is just X base change to ZP zeta P. That'll be a formal scheme over ZP zeta P for which I could contemplate this theorem. And the group of the Galois group, FP star, acts by raising that P through to unity to powers. And if we prove the theorem is true for Y, we'll get a pullback square of chain complexes with an action of that Galois group. We can take fixed points for that Galois group, and we will recover the complex, that same diagram that we would have associated to X. So there's no harm in adding this P through to unity, and actually, I'm gonna argue there's something to be gained. We're gonna be able to say something a lot more precise. So let me actually, this is a case of what I said, the situation I mentioned earlier, where we would have ramification index less than P. The ramification index here is P minus 1, which means that actually all of the maps here that you want to contemplate, they're not just defined rationally, they're defined integrally. So you can consider R gamma of X, dP of N, and this maps to, well, first R gamma of X naught, ZP of N. It maps to R gamma of X with coefficients in differential forms of degree greater than or equal to N, and some homotopy fiber product with the entire. I'm now omitting all of these symbols left to right and hat. They're supposed to be there, but my wrist will get tired. Okay, so this is a map which is defined integrally, and the claim is that the not only is this rationally an isomorphism, I can tell you what denominators you need. So let's say the cone is annihilated by p to the n plus 1 times n factorial. And actually, I would like to first explain what this n plus 1 is doing here, and then make an even more precise statement than that. So what's going on here? So this map here, R gamma of x naught z p of n, this is the Syntomic cohomology of the special fiber, which is some Frobenius fixed part of the crystalline cohomology of the special fiber. And that has a comparison map to de Rham cohomology, and that's because of the miracle of crystalline cohomology that just the special fiber of X already knows the de Rham cohomology of the entire scheme. But what this diagram is telling, or why this diagram is interesting, is that although it knows the de Rham complex, it doesn't know the Hodge filtration on the de Rham complex. But it knows a little bit of the Hodge filtration of the de Rham complex, because certainly the special fiber of X knows what the Hodge filtration should be on the de Rham complex of the special fiber itself. So let me try to make a slightly more refined statement, which takes that into account. So let me draw a slightly more complicated diagram that we have in this situation. We can look at the Syntomic cohomology of X. Now let's say with integer coefficients. So this certainly maps to the Syntomic cohomology of its special fiber. Which maps to the de Rham cohomology of X. Call that omega star X. But it also maps to the nth stage of the Hodge filtration on the de Rham cohomology of X0. And here, this X is over OK, and this is over, that's relative to the residue field. And there's a compatibility, which that these two maps agree after we map both of those things into the de Rham cohomology of the special fiber, but we don't keep track of the Hodge filtration. I'm going to get X0 over K. And another thing that maps into that fiber product is just the appropriate stage of the Hodge filtration on the de Rham cohomology of X. So I want to give the fiber product here the limit of everything except the upper left-hand corner. I'm going to give this a name. So the limit of this circle part, I'm going to call R gamma split of X z here. So R gamma split, it's something which maps to this fiber product here. And the more precise statement that I want to make is that the theorem, this map to R gamma split X z p of n. The cone is annihilated by p to the n times. So I introduced a slight correction, but the correction rationally doesn't matter. It's all about the special fiber, and it's all annihilated by p. And so the philosophy of this should be like this right-hand side, that's the smartest approximation that maybe someone could think of if you wanted to make some kind of universal cohomology theory out of classical ingredients. You know about crystalline cohomology, you know about de Rham cohomology with its Hodge filtration. Just take all of those ingredients, try to make some inverse, try to take some inverse limit. Well, that's not Syntomic cohomology, but it's not far off. That's what the theorem is saying. Okay, so
Can you show what this is again?
It's the fiber product of the Syntomic cohomology of the special fiber, stage of the Hodge filtration on the Rham cohomology over this fiber product. It's a limit of 5 things. I'll send it up and bring this down. Now the theorem's gone, but you can't have it. All right, so how long have I got now? 20 minutes. Okay, so I want to, in those 20 minutes, I would like to sketch something of the proof of this theorem. So
Is the saving of P very clear?
is the statement,
The saving of P by kind of given. I mean, I mean you kind of introduced this split and you got a saving of P, you got dpf on N.
Yeah.
But I don't think you said why you got a saving of P.
well, I've stated a stronger theorem.
Yeah.
The theorem with the p to the n will imply the theorem with the p to the n plus 1 because you're off by a thing that's annihilated by p.
Yeah, but that's a saving of P you didn't expect. There's a hard saving.
No, I've made it. I'm not deducing the second statement from the first.
I know, but yeah. Never mind.
Okay, so I want to go on a little bit of a digression. So I said that I was going to give you a proof and it's going to be different from the preceding proofs. I'm not going to try to exploit the relationship of these invariants with algebraic K theory. What I want to do instead is really exploit this point of view of Drinfeld, that Syntomic cohomology is about the coherent cohomology of these auxiliary geometric objects, and this statement is a consequence of something that's happening in the geometry of these auxiliary objects. So let me say a few words about this point of view. So recall, or learn now, if you didn't take Bargo's course, I apologize for that, to any sufficiently nice p-adic formal schemes you can associate that I'm going to write as x setting. And this is functorial in X. So now the X's that I'm interested in are going to live over ZP beta P. So in the situation that I'm interested in, this is going to map to spoof ZP zeta P sin. And well, just to save chalk, we just call that ZP zeta P sin, removing the split part. And now this complex R gamma of X, the Syntomic complex of X with weight n. Well, maybe this is the definition, or maybe this is a theorem about why this stack is interesting. This is R gamma of X sin with coefficients in some line bundle. Get right as till then. And let me call this map pi. So another way that we could write that, it's the coherent cohomology of ZP zeta P sin with coefficients in a certain sheaf that I'll write as E sub x, with twisted by a certain line post. And here E sub x is just going to denote the push forward of the structure sheaf of X along this map. Okay, so this is just a formal manipulation. So I want to explain why is this a valuable point of view? Why is it useful to think of Syntomic cohomology as given in 2 steps this way, given by first building some sheaf on ZP zeta P sin and then taking the cohomology of that sheaf. And the way that I think about it is that Syntomic cohomology does not satisfy a Künneth formula. There's nothing that tells you that if you want to compute the Syntomic cohomology of X cross Y, you just take the Syntomic cohomology of X and the Syntomic cohomology of Y and tensor them together or something like that. And that's exactly what you would expect if this was something capturing information about algebraic cycles. Like, there are typically going to be lots of algebraic cycles on x cross y that are not explained in terms of cycles on the individual factors. So Syntomic cohomology doesn't have a Künneth formula. And from this point of view, the reason for that is that this stack, ZP zeta P sin, is not affine. There's information lost by taking global sections. So there is a local Künneth formula. By which I mean that if you want to take x cross y, and here I'm doing this over the base ZP zeta P, then this factors as the tensor product of E sub x and E sub y, but this is happening in the derived category of sheaves on this stack. So that's the sense in which Syntomic cohomology satisfies a Künneth formula. But it's sort of not visible if you just think about Syntomic cohomology as something that gives you groups or something that gives you chain complexes. It's visible when you think of Syntomic cohomology as giving you something that's spread out over this stack ZP zeta P sin. So let me say that a slightly different way and then exploit it. So philosophy. Is that this object ZP zeta P sin classifies cohomology theories on ZP zeta P. I should say formal ZP zeta P schemes. And well, not all cohomology theories, but cohomology theories that kind of behave like de Rham cohomology. So let me make that a little more precise. So let's say you had a map from spec R into this object ZP zeta P sin. Then you could consider the construction where you input a formal scheme over ZP zeta P. Now, associated to that is this object E sub x, which is some object in the derived category of this stack. And then you could pull it back along this map. Now, this is something which lives in the derived category of the ring R. And the thing that I'm saying here about having a local Künneth formula means anytime you have an R-valued point, this gives you, you can think of this as a cohomology theory valued in R modules. You input a formal scheme, it outputs a complex of R modules, and that construction satisfies a Künneth formula. It takes products of schemes to tensor products of complexes.
Sorry, Jacob. Yes, and Y are fine.
X and Y are, they don't need to be affine, but they should be like QCQS. Yeah, I mean, just as in topology, you won't have a Künneth formula for cohomology if you allow things that are too infinite, but they're quasi-compact and quasi-separated. Okay, so this is, so every R-valued point of this stack gives you a cohomology theory for which you have a Künneth formula. Syntomic cohomology is not one of those cohomology theories. It's the inverse limit of all of them. And each one of those individual cohomology theories has sort of a coefficient ring R that you have to take tensor products over. But when you take the inverse limit, there's no global R. And that's why you don't have a Künneth formula in the end. So that's maybe one reason that you might be interested in this point of view. So let me just give an example of what that's saying. So let's say we're interested in the Syntomic cohomology not of X, but of its special fiber. So the Künneth formula tells us how to compute this. Right? So X0 is something that we can write as X cross spec of the residue field over spoof ZP zeta P. So the Künneth formula will allow us to rewrite this again. I can write this, it's R gamma cohomology over this stack of E sub x tensored with something, which is E sub spec k. And then a twist, depending on what weight I'm interested in.
What I've seen.
What's that? Oh, set, yeah. And now let me just mention, is it still here? Yeah, so every term in this diagram has a similar flavor. You want the upper left-hand corner, you take the cohomology. So I'm always taking cohomology over ZP zeta P sin. Over here, you take the cohomology of EX. Here you take the cohomology of EX tensored with some fixed thing, which is E of spec k. And every other term in this diagram has a similar description. You take EX, you tensor it with some fixed thing that doesn't depend on X, and you take the cohomology of that. So without going into details on that, let me just give you the upshot. The upshot is there's a formula for what I've called split syntomic cohomology. This approximation to syntomic cohomology made out of classical ingredients. It has a similar description. It can be computed as the coherent cohomology over ZP zeta P sin of, well, something that depends on X, and then some twist that depends on the weight. And well, if I just stop there, that would be the syntomic cohomology of X, but split syntomic cohomology, first I tensor it with some algebra A, and then I take local cohomology. And the comparison map that we're interested in is coming from syntomic cohomology, and that just has the same formula. It's just that I omit the A. I just take EX twisted by N here. And so the theorem that this map is a rational isomorphism, I want to deduce it from something having nothing to do with that. It's about A. It's about the structure of this particular sheaf on ZP zeta P. So let me tell you structure and then tell you why that implies the theorem. Call this a proto-theorem. More primitive version of the theorem. A has an increasing exhaustive filtration. First step is fill 0 of A is the structure sheaf of ZP zeta P. Then that goes to fill 1 of A, fill 2 of A, and so forth. And I'll tell you the associated gradient of this filtration, N of A, looks like you took the structure sheaf, you reduced it mod P times N. Oh, actually, why don't I write D of A? Modulo PD, and then you twist by minus 2. So let's say you believe the proto-theorem. Let's draw a corollary of that. Well, if you're interested in the split syntomic cohomology of X with ZP of N coefficients, this has a filtration where Phil naught is the thing that we are originally interested in. Phil naught is usual syntomic cohomology. And D looks like the syntomic cohomology of X, now with coefficients in ZP reduced mod P times D, and with a twist, which is N minus D. And let me just remark, Syntomic cohomology, when the twist becomes negative, it's just 0. So this is 0 for n, sorry, for d greater than n. So this is a finite filtration. The filtration of A is infinite, but when you use it to say something about any given x, or to say something about Syntomic cohomology in a given weight, you end up with a finite filtration on Syntomic cohomology. And you see here from this description, this is annihilated by p times d. And so if I take all of the graded pieces that appear and take an extension of them, I get something that's annihilated by p to the n times n factorial. Okay, so how long have I got now? Only not much time. Okay, so let me just say some very brief words about how you might come to know this about A. How could you know A has a filtration like this? So first, let me remark that this is saying something very special about the structure of A. You might wonder, why did I want to make that funny correction about the Hodge filtration mod P? If I hadn't made that correction, everything that I would have said up to the point of stating that proto-theorem would have been fine. I just wouldn't have been able to tell you anything about the structure of A. But if you make just the right definitions, then you can say you need a very special sheaf on ZP zeta P sim. So philosophy is that this is this category of sheaves on ZP zeta P sim, called the category of prismatic F gauges. It's some p-adic version of some version of motives for p-adic formal schemes, or in this case, p-adic formal schemes over ZP zeta P. And A, in particular, you can think of as some kind of p-adic motive, but it's a motive of a very special type because I've written it with a filtration like this. It's like the analog of a mixed Tate motive. It's made out of pieces that involve the cyclotomic character. Okay, so let me give a very impressionistic last few seconds explaining where this picture comes from. So prismatic F gauges over ZP zeta P. There's a prismatic F gauges that satisfy some finiteness condition give you Galois representations for the field K, which in this case is QP zeta P. There's a forgetful functor from, let's say, coherent sheaves on here to ZP modules with a continuous action of the Galois group. And you don't see all Galois representations this way. You only see Galois representations that are, well, crystalline when you invert P. So the philosophy is that this is a, so let me put this in quotation marks. This is a formal model or the classifying stack B of the Galois group. Here I'll just write QP zeta. So you can kind of think the classifying stack of this Galois group, where sheaves on this classifying stack would just mean representations of this Galois group. This classifying stack, in some heuristic sense, sits inside this thing as a kind of generic fiber. And now, what I'm saying over here is in particular telling you that when you think about A, you don't see very complicated Galois representations coming up. You only see Galois representations which in some sense come from the cyclotomic character. So there's a map coming from the cyclotomic character that goes to B of gamma. So here gamma, by gamma I mean 1 plus PZP sitting inside ZP star. Now, since I've given myself one p-third unity, that's where the cyclotomic character for this field lands. And, well, there's another object, which I sort of fancifully call F1 adjoins zeta P sim, which I'm not going to define for you here, but I gave a lecture here a few months ago, or maybe more than a few months ago now, in which I defined an object closely related to this, which is it plays an analogous role, which is that it's a formal model, not for the Galois group, but for the target of the cyclotomic character. And now, Galois representations are hard, but Galois representations that factor through the cyclotomic character are not that hard. Gamma is a very simple group, right? When p is not 2, that's just isomorphic to zp by the logarithm, and there's not much to say about its representations. And, well, let me say there's a map from this object zp zeta p sin to this other object. And this A that I've said here, it's made out of, let's say, representations that come from the cyclotomic character, and actually all the extensions that appear in some sense also come from the cyclotomic character. Or a more precise statement is that it's the pullback of a certain algebra A0, which lives in this category. And now, let me just, over time, but this will promise this is the last thing. This category is very simple. So let me just, the derived category of this F1 zeta p sin. Let's say it's approximately filtered complexes M. With the gamma action such that gamma acts for nm by the identity character to the nth power. And under this dictionary, the object A0 that I'm talking about is a very obvious thing. It's QP, if I ignore the filtration, where I declare that fill n of A0 is, well, 1 over p to the m times n factorial times zp. So it's the trivial representation of gamma on QP, but thought of as a crystalline Galois representation in an interesting way in some sense. The integral level, I'm taking an interesting filtration. And that formally implies this statement about A. All right, I'm already over time. Thank you very much.
Questions?
So in this diagram, this photo diagram, so the formal scheme has to be a finite cars.
This, no. This is,
No.
no.
Okay, another question is,
Oh, sorry, I should remind you to repeat the question.
Oh, sorry, the question is, sorry, it's about the original theorem. The original theorem doesn't require any finiteness conditions on X, with the caveat that, you know, if you want to allow non-Noetherian things, then you should be a little bit careful about unbounded p-torsion. When you want to take the special fiber or something like that.
okay, and is this an invariant, the Syntomic Cohomology, X is singular? I mean, is it invariant of the generic fiber?
No, I don't think so.
Question there.
Oh, sorry, the question is, does symptomic quality depend only on the generic fiber? Well, sorry, that.
So you really have to introduce logarithmic structures to actually get that, or?
Well, sorry, the version that I'm talking about is, if you wanted to get a good invariant for like open varieties that have reasonable finiteness properties, that's not what I'm talking about. The thing I'm talking about would be like, you know, if you put in the affine line over FP, I'm taking the de Rham complex, not some kind of log de Rham complex at infinity. So
No, I was more thinking about depends on the generic fiber or the rigid generic fiber.
the rigid generic fiber, I do not, I mean, no, it definitely doesn't depend just on the rigid generic fiber because it's a non-zero invariant if you put it in FP schemes.
Right. But if it's flat.
If it's flat, I would not think so.
Can you say again how gamma acts on A0?
Gamma acts on A0 trivially. So maybe say something about these denominators that appear. So in order to satisfy this condition, I cannot put an arbitrary filtration here. Let's say I decide Fil0 is going to be ZP. Now, on GR1, this has to act by the identity character, but it also has to act trivially, which means that the difference between Fil0 and Fil1 can be at most P.
Is this one place where the package ZP equals zeta P?
What's that?
I mean, you introduced zeta P.
I believe that it's crucial.
I mean, it wasn't clear to me like where that was being used. But it's clearly being used here.
So,
What they
well,
gave
it's
The
being
question-
used as, so if I started with an arbitrary K, let's say a ramification index less than P, I could define an analog of this A. I would then have nothing to say about A. For example, I can define the analog of A for K equals QP. I don't know how to tell you anything interesting about that A. It's this particular extension, I can tell you that it kind of comes from this more primitive place where you can do calculations with linear algebra.
So if you hadn't made the split modification, then also it wouldn't descend that.
You mean if I had taken the limit of 3 things instead of that limit of 5 things?
Yeah.
Yeah, so then there would again be an A. It would be slightly different from this A. I do not think it would be pulled back along this map, and I would not be able to analyze it.
If no more questions, let's thank Kate again.